So today we're pleased to have Gurtina Besla give the CFA colloquium. So many of you know her quite well. She was a student here, but let me just give a brief introduction. So Gurtina finished her thesis 2 years ago, and then she moved to Columbia as a Hubble Fellow. And just last year, after having been there for just a little over a year, she was offered and accepted a faculty job at the University of Arizona. And I think that's a pretty significant achievement for anybody, but amazing considering how young she is in our field. Not surprisingly, she's gotten a lot of recognition for her work. So for example, this past year, she was awarded the Trumpler Prize, which is given annually by the Astronomical Society of the Pacific for a thesis in astrophysics they consider to be particularly important. And for her thesis, she developed, based on work done by Charles Alcock and Nitya Kalibayalil, a new dynamical model for the orbital history and evolution of the Magellanic Clouds and the Magellanic Cloud system. And this model has made a number of interesting predictions about not just the orbits of the clouds, but the origin of the Magellanic Stream and the internal properties of the large and small Magellanic Clouds, and has stimulated a lot of new observational work in this area, all of which goes in the direction of confirming the picture that Gurtina developed. And in addition, she's developed other kinds of interests based on her work, and so today she'll tell you about some of the outgrowths of her thesis work, which is new and different, dealing with dwarf galaxies. Gurtina?
Great, thanks so much for the introduction, Lars. This on, and everyone can hear me all right? Wonderful. So the study of dwarf galaxies is a rapidly growing field. There are many new studies and surveys of dwarf galaxies as a population, particularly how are dwarf galaxies evolving over time? What are their baryon cycle? What is their star formation rates? And the idea of the term dwarf galaxy specifically means a low mass, low metallicity system, but this is a broad term. And so necessarily the study of dwarf galaxies is a very broad field. So what I'd like to do in this talk is to discuss some of the hot topics in dwarf galaxy evolution right now. Why is the field growing so rapidly? And then also discuss a number of different types of dwarf galaxies that are encompassed in this definition. Some are shown at the top here: dwarf spheroidals, dwarf irregulars, dwarf ellipticals, dwarf spirals. What are all these terms and how are they related, and particularly in an evolutionary sense? And I want to draw your attention to particularly star-bursting dwarf galaxies and how they can be linked to interactions between dwarf galaxies themselves. These are two dwarfs, an LMC analog and an SMC analog, that are in the midst of a tidal interaction. And you can see tidal perturbances in the larger galaxy starbursts that are undergoing because of these interactions. And I will argue that these types of interactions are not necessarily uncommon and can be quite damaging to these systems. So first of all, what is a dwarf galaxy? So like I said, low mass, low metallicity system. But that's a pretty broad definition. And in general, people have thought about it in terms of an absolute, limited in terms of the absolute visual magnitude. I've adopted a value of galaxies fainter than -19 in visual magnitude, and so it's still a very broad definition. But when we talk about definitions for galaxies, we want to point to something more physical. And so what I would actually rather adopt is a cut in the rotation curve of a galaxy. I would state that if a galaxy has a rotation curve that peaks at values less than 100 kilometers per second, that would be considered a dwarf galaxy. If you use the baryonic Tully-Fisher relationship, 100 kilometers per second then corresponds to a baryonic mass of about 5 by 10 to the 9 solar masses, and at the upper limit of this regime, this is basically stellar mass. Now, of course, these galaxies need to be galaxies, and in that sense, they need to have some evidence for a dark matter halo, and this can be seen from the rotation curve, or it can also be seen from the velocity dispersion profiles of, for example, dwarf spheroidals. Now, if you take these kinds of cuts, then you will ultimately get low metallicity systems with iron abundances of less than -0.4. Basically, metallicity is around a third of solar or lower, and those are the dwarf galaxy population. So by these definitions, the LMC, which is the largest satellite galaxy of the Milky Way, would be considered a dwarf galaxy. Its rotation curve peaks at about 85 or so kilometers per second. M33, however, which is the third most massive body in our local group and the largest satellite galaxy of M31, would not be considered a dwarf. Its classification is actually a spiral galaxy, and you can see a very large difference between the structure observed in M33, which shows very symmetric, regular spiral structure, versus something like the LMC, which is a bit messed up. Certainly spiral structure, but this is highly amorphous and highly irregular. Now, what happens, and again, I'm not trying to make a classification that's completely arbitrary. What I am arguing is that by making a limit on the rotation curve, I'm essentially saying that there is a fundamental difference when you go to low mass halos. When you have halos that have potentials where the rotation curve is less than 100 kilometers per second, these low mass potentials indicate that different physics is going to be going on. So first example, a low-mass halo will be more prone to tidal perturbations. So the LMC, for example, is very easily perturbed by interactions with a low-mass companion like the SMC, whereas M33, which is in orbit around M31, is not really all that perturbed in comparison. Also, with a lower mass halo, galactic outflows, ram pressure stripping, all those factors are much more efficient than they are for more massive galaxies. And in particular, because galactic outflows are so efficient, you lose metals from these galaxies very rapidly. And that explains why the metallicity for these galaxies are really low. So I do think that we're coming down to really pinpointing the physics, that there's actually a difference in the physics of galaxy evolution for low mass halos versus larger mass halos, or smaller galaxies versus larger galaxies. And that's why I think that the dwarf galaxy regime is a distinct regime in terms of understanding galaxy evolution. So for overall in my talk, I want you to come away with 3 points. The first point is that gas-rich, star-forming dwarf irregulars and gas-poor dwarf spheroidals are in fact intimately linked in that they actually obey similar scaling relationships. So there is a reason for why we believe there may be some sort of evolutionary links between these two classes of galaxies, from gas-rich to gas-poor. The second point is that this type of evolution, gas-rich to gas-poor, is being driven by environmental factors. Ram pressure stripping, tidal stripping, those are really what's driving it, rather than things like outflows. But I will say that a massive central galaxy is not a necessary condition to create a quenched dwarf. In fact, you can create these kinds of transitions in dwarf galaxy environments, so that you may have, for example, a LMC-type analog massive dwarf galaxy and a smaller companion nearby that is undergoing morphological transformation, tidal stripping, and also losing its gas. And I'll talk a little bit more about this system later. The third point that I want you to take away is that interactions and mergers between dwarf galaxies can drive starbursts. And this is a class of galaxies referred to as blue compact dwarfs that are in the process of starbursting. But this whole process, this merger sequence of dwarf galaxies, appears to be distinct from the merger sequence of more massive galaxies. In particular, we don't think that dwarf galaxy mergers would result in a gas-poor spheroid or a quenched system. But this is a really open area of study. There's very little data, very little work, either on the theoretical front or the observational front on this topic. And this is my current area of research. All right, so like I've said, it's a growing field. And this is an evidence of just the number of surveys that are devoted towards studying dwarf galaxies. In our local group area, there's been an awful lot of work on dwarf galaxies in general. It's the most dominant, obviously. There's a lot of satellite galaxies in our local environment. But specifically, there's been a recognition that dwarf galaxies can serve as probes or tests of cosmological predictions, this idea of near-field cosmology. And so you have surveys like the PANDAS and the SPLASH survey, which are focusing on the dwarf populations around M31. SDSS has revealed a lot of information about our own galaxy's satellite population, and certainly Gaia will tell us more. And in the theoretical side, there have been simulations of Milky Ways type galaxies in a cosmological context, like Via Lactea, the Aquarius suite of simulations, Eris, that includes gas in addition to dark matter. And so what we're doing here is, there's a buildup of synergistic intertwine between observations of dwarf galaxies in the local group and cosmological predictions for their, for example, the number density or the missing satellite problem, the properties of the dark matter profiles, i.e. the cusp core debate. So there's been a lot of interest in dwarf galaxies in the context of cosmological probes. But I would say that right now what's happening is that the field has expanded beyond that. And there's a suite of surveys, for example, that are focusing on dwarf galaxies out to 10 megaparsecs or so, somewhere between 4 and 10. There's HST data looking at in detail the star formation histories of these galaxies using resolved stellar populations. There is the 11 Hug survey, which is looking at starbursting dwarfs and some of the most extreme star formation events. There's H1 surveys looking at the rotation curves of galaxies at very large distances of these dwarf systems, the little things, the faint irregular galaxies using GMRT and VLA. And then there's the Herschel survey of dwarf galaxies in particular, looking at the dust properties of these systems. What's happening is that there's a large suite of observational surveys that are trying to understand the properties of the ISM of dwarf galaxies as a population. Right? Just the interest is on dwarf galaxies themselves, not in terms of as probes of larger galaxies or as probes of cosmological properties. Now, going out to even larger distances, out to 100 megaparsecs, there are also surveys that can give us populations of dwarfs. SDSS, the Gamma survey. Avocado is a survey that's been using SDSS and mining it out to 20 and 60 megaparsecs to understand star formation rates and properties of dwarfs on those scales. And there are cosmological volumes that can also provide counterparts to these surveys to these distances. Bolshoi, Millennium 2, which are dark matter only simulations, that can have sufficient resolution to go down to an SMC mass scale, for example. And I would like to introduce a survey that I'm working on. I've referred to as the Tiny Titan survey, and the name's subject to change. But at any rate, right now, it's a survey of interacting dwarf galaxies in isolated environments. And what we've done is looked at interacting pairs of dwarfs or groups of dwarfs in Sloan, and then selected them for multi-wavelength follow-up using GRI, H1, we have VLA, Arecibo, GBT. There's so many different programs that we have ongoing to basically get a multi-wavelength view of interacting dwarf galaxies that are far away from massive hosts. And at the same time, we're also using the Illustra simulation, and if you were here at the ITC luncheon earlier, you'll have heard Mark Vogelsberger talking about this. This is in-house at Harvard, to look at dark matter and baryons in a cosmological context in the buildup and evolution of dwarf galaxies, particularly how this relates to the frequency at which dwarf galaxies interact with each other and how that compares to observations. So there's an entire suite of studies that are looking at dwarf galaxies as a population, what happens when they interact, what are their star formation rates, gas densities, et cetera. And I think the reason that this is happening, the reason there's been a switch in the viewpoint in the field, is because of a recognition of three things. The first thing is that star formation and dwarf galaxies are basically probing metal-poor environments. And so star formation in those environments is probing metal-poor prescriptions. As the metallicity of a galaxy goes down, the dust content goes down. And H2 formation needs dust. And so as a result, H2 formation in these low metallicity systems is quite inefficient. So there's been a recognition in the field that star formation prescriptions need to account for H2 formation explicitly. If you were to follow a Kennicut-Schmidt relationship, for example, and just say that the star formation rate should follow gas density, then you're going to overpredict the number of stars that should be produced in a dwarf galaxy. And so there's been a large number of work of theoretical studies on how you would account for H2 formation explicitly in low metallicity regimes. So there's already a spawning of work on this study. But if you're going to test any of these models, then you have to go to the dwarf galaxy regime. Furthermore, when you go to dwarf galaxies, you can probe some of the lowest metallicity systems that we know of. This is Wiki 18. It is a dwarf galaxy that's in the middle of a starburst. It's all concentrated in this tiny region over here. And its metallicity is about a tenth of solar. It's extremely metal poor. And so what's happening is by probing the star formation properties in the ISM in systems like this, essentially we're probing and exploring the star formation ISM relationship in conditions that are approaching those of the earliest and most metal poor galaxies, right? So we're trying to probe and understand star formation at a much higher redshift through studies of these systems. So second point that I wanted to raise is that not only are we probing star formation in very extreme metal poor regimes, but generally speaking, the star formation in these galaxies is just extreme. So if you think of the LMC, this is our closest gas-rich dwarf galaxy, and this is shown face on, this is an H1 distribution. You see all these holes that are marked with circles. So these are created by past star formation events. And you can see that they're creating these massive supershells. Now these shells are, if you think of the size of this relative to the size of the galaxy, and in some smaller systems, the size of these shells relatively could be about half the size or a quarter of the size of the galaxy itself. What this means is that at this regime, you cannot disentangle local star formation events from a global mode. Right? When you're really talking about star formation in dwarf galaxies, you're talking about individual star-forming regions, and these individual regions will have an impact on the global morphology of a dwarf galaxy. So going back to the LMC, this is here in H alpha, and you can see the 30 Doradus region, which is the largest H2 region that we know of in our local environment. Right? The 30 Doradus region can hold 75 Orion nebulae. Right? I mean, it's massive. It's like 200 parsecs and a million stars. And it's basically a local starburst going on inside this larger galaxy. And when we talk about the star formation rate of dwarf galaxies, we're not talking about a global mode of star formation. You're really talking about systems like these with a large H2 region forming stars. Again, to Wiki 18, is all the star formation is going in one quadrant of this galaxy. And what's interesting from a computational and theoretical point of view is that we can start to actually draw links to work that's been done about individual star-forming regions. So the work, for example, Alyssa Goodman's been doing here and Stella Offner from a theoretical point of view, and linking that on those scales to a global mode of star formation. And this is only really possible in the dwarf galaxy regime in any kind of computational way because these systems are small. So you can imagine that we would be able to, in the near future, watch the evolution of a star-forming region in one section of a galaxy disk, the size of a dwarf galaxy, and understand its global mode of star formation in that way. So trying to draw links. So the third point that I think is really what's changing the viewpoint of dwarf galaxies and really pushing the field is something that we've known for a really long time, and that is that dwarfs are the most numerous class of galaxy in our universe. So this is a plot that's showing you the space number density of galaxies as a function of central surface brightness. And so we know that there are very few galaxies at high central surface brightness, and so this falls off. And then there was this viewpoint back in the 1970s that all of these spiral galaxies sit at a constant surface brightness, and there really are nothing over on this low surface brightness end. Of course, this is an observational bias, and as we have surveys that have started to probe this regime, it seems more likely that this distribution flattens off. And you can actually have more than 50% or so of galaxies are in this low surface brightness regime, which is predominantly dominated by dwarfs. Now, this is basically telling us that, if you really want to understand galaxy evolution, we should be including dwarfs in this context, right? Since it comprises most of the population of galaxies. This is where all the stars are forming today. But I think it's reasonable to understand why there hasn't been a lot of focus on dwarf galaxies as a population, because they're faint. I mean, we haven't had, until the advent of Herschel, a way of really probing, for example, the dust properties of galaxies in these mass regimes. So it's a new field, it's a growing field, and this is just because we have now simulations that can probe these mass scales, and we have surveys that can go out to large distances and probe these low surface brightness galaxies. Okay, so that's kind of, at least I hope I've made the case of why dwarf galaxies is an important field and a growing field. And I want to talk more about the different classes of galaxies. So this diagram is showing you all different types of galaxies plotted with their absolute visual magnitude relative to their central surface brightness in V-band. Okay, so elliptical galaxies reside in this section of this diagram. They all have very high central surface brightnesses and are bright galaxies, right? And the spiral disk type galaxies lie over here, roughly constant surface density. Galactic globular clusters are very faint, but they're also quite compact, right? So they reside over here. Over here is a population of what they call UCDs, or ultra compact dwarfs. I'm not really going to talk about them. They only reside in clusters. They're basically, potentially, we don't really know what they are. They're really compact objects, potentially the nuclei of dwarfs that have been severely processed. So that's a different kind of beast of object. But what I really want to talk about is over here. So dwarf galaxies, as I said, are galaxies that are, have visual magnitudes fainter than -19. And they have, rotation curves that peak no more than 100 kilometers per second. But another part of the definitions is that dwarfs share a very well-defined relationship between the absolute magnitude and the central surface brightness. They have a scaling relationship that seems to be obeyed by all different classes of dwarf galaxies. Right? And this is, again, why we think that there are probably links between the gas-rich and the gas-poor galaxies, because they seem to all lie on the same regime. So here, this yellow type hexagons are galaxies without gas, and then the blue ones are ones with gas. You can see they all kind of overlap on top of one another. So I want to talk about these different classes of galaxies in a bit more detail. So the first one, and kind of the newer type of galaxy that's been discovered, is the ultra-faint dwarfs. So these galaxies reside over here at visual magnitudes fainter than about -7. They have stellar masses no greater than 10 to the 5 solar masses, and some have only a few hundred stars in them. But they are distinct from galactic globular clusters in that, as you can see, their central surface brightnesses are a lot lower, so they're a lot less compact than a globular cluster. So if you really were to think of them not as a galaxy, but rather perhaps a more extended globular cluster, then you would expect their central surface their velocity dispersions to be lower than those of globular clusters. But in fact, that's not the case. The central surface, the velocity dispersions are between 2 and 7 kilometers per second, implying mass-light ratios on the order of 1,000. Now, what's really interesting about these galaxies, very recently, there's been this paper by Tom Brown. So what's shown here is a color magnitude diagram of 6 ultra-faint dwarfs plotted on top of one another. They're all scaled to the distance of one of these ultra-faint dwarfs, Hercules, which is the most massive one. And now what Tom has found is that all of these, their star formation histories, or their color magnitude diagrams, imply that they are dominated by an old population that is older than 12 billion years. And so this is a population that is very interesting in the context of a cosmological probe, because this is probably probing the epoch of reionization. What's also striking is that all of these color magnitude diagrams lie right on top of one another. And we wouldn't expect necessarily to have a similar, unless the luminosity difference between the main sequence turnoff and the horizontal branch has to be the same with all of these different color magnitude diagrams in order for this to work out. So what this is implying is that the star formation histories are similar, and that quenching occurred at roughly the same timescale within about 1 billion years of each other. So it was a synchronized star formation history. So star formation shut off on these galaxies roughly around the same time, and this is likely the epoch of reionization. So when we talk about ultra-faint dwarfs, we are likely talking about the true fossil records of the early universe and the earliest phases of dwarf galaxy evolution or galaxy evolution. In that sense, I think that these galaxies are distinct from the other galaxies that I'll be talking about. And so they're not really taking part in this evolutionary change between gas poor and gas rich. I think they really are, it's just representing a lower mass limit in terms of galaxy evolution. Okay, so moving on to galaxies, kind of stepping away from the ultra-faints, now going to a regime between, let's say, the ultra-faint limit was visual magnitudes of -7, so let's go from -7 to the limit of -19. And I want to talk about the gas-poor dispersion-supported systems. These are dwarf spheroidals and oftentimes also called dwarf ellipticals. Dwarf spheroidals, I'm going to put a limit out here, and I'll show where the dwarf ellipticals are. Okay, so dwarf spheroidals are, generally speaking, lower in mass. Dwarf ellipticals are basically just more massive dwarf spheroidals. Now, they're called dwarf ellipticals, and again, this is one of the things astronomers do, where we name things and make things confusing. These are not actually lower mass elliptical galaxies. They're very distinct in that they obey a very different scaling relationship between central surface brightness and visual magnitude, right? So they're different types of galaxies. What's interesting about these systems is that dwarf elliptical galaxies are in a mass regime here where we can probe galaxies out to more than 4 megaparsecs. So we have a census of these kinds of galaxies out to very large distances. And what we find is that you never find dwarf ellipticals in the field. You only ever find them in very clustered clusters or around massive galaxies like M31. So M31 has 3 of these galaxies, whereas the Milky Way has none. And that's an interesting point just in general in terms of differences between the satellite populations of M31 and the Milky Way. The Milky Way has the M31 has 3 fairly massive gas-poor spheroidal type systems, and the Milky Way has just a number of smaller galaxies out here. Okay, so dwarf ellipticals also in some cases can have a bit of gas. This is probably again an indication of their higher mass. They're able to retain that gas a little bit longer. Let's talk now about dwarf galaxies that have gas. So these are your dwarf irregulars and your dwarf spirals. An irregular galaxy basically means a galaxy without ordered structure. So star formation proceeds in a very stochastic manner in these galaxies. You don't get spirals or bars or bulges. You get kind of just a mess, really. Dwarf spirals, in that sense, are really more massive versions of dwarf irregulars where you start to get more structure. And they kind of build into your disk-type galaxies. So an LMC would sit over here, whereas most of these gas star-forming galaxies are dwarf irregulars, kind of spanning this full range in mass. Now, an interesting population of galaxies is referred to as BCDs. These are dwarf irregulars that appear to be going through a starburst phase. So their star formation rates are 3 times larger than their average star formation rate. These are generally very compact objects, and I'll talk more in detail about these galaxies. So in general, we're able to probe out to large distances the populations in this regime here, dwarf galaxies. But over here, dwarf spheroidals in particular are really limited to within 4 megaparsecs and basically our local group environment. So we don't really have analogs out in the field for what these systems are. So as I mentioned, there's the scaling relationship between central surface brightness and visual magnitude that is obeyed by both the gas-rich and the gas-poor dwarfs. But another relationship is also obeyed by all of these galaxies, and that is the luminosity-metallicity relationship. So here, as you go to more massive galaxies, you'll find the SMC, the LMC out here, and then there are a number of, so in the red are indicating M31 dwarfs. The circles are indicating Milky Way dwarfs. These are all spheroids, no gas. And then in the blue are some of the local group galaxies which have gas. So you can see they all follow the same relationship, which again suggests that they have similar overall evolution, and the difference seems to be right now in terms of their gas content and star formation rates. This relationship exists because of outflows, most likely. These galaxies are losing metals very efficiently through star formation. So this, again, I said, these are low-mass halos. Stellar outflows are quite efficient at removing metals. As you go to higher masses, they become a little bit better at holding on to their metals, and so their metallicity is a little bit higher than it would be at the low-mass end. What's interesting is that if you think of a galaxy out here that's being tidally stripped and not be thinking about its gas content or evolution and metallicity in any way, you would then move over this way in this diagram. And so you can see that, for example, the Sagittarius dwarf does seem to rely over to this side of this relationship. The Sagittarius dwarf is a very tidally stripped system and may have once been a more massive galaxy in the past. I'll talk a bit about that in a second. All right, so we have these scaling relationships that suggest that there is an overall similar evolution between dwarf irregular galaxies and dwarf spheroidal galaxies, gas-rich and gas-poor systems. But where you really get a deviation between these two classes of galaxies is when you look at their gas content as a function of their separation from their hosts, either the Milky Way or the M31. This is specifically for the local group. And we find is that all the gas-poor, ultra-faint dwarfs and dwarf spheroidals, et cetera, are all within the virial radius, whereas all the dwarf irregular galaxies are basically sitting at the virial radius or beyond. And this is really telling us that there's a very strong environmental dependence on the evolution between the gas-rich and the gas-poor systems, right? So it's not necessarily, so what's really happening is the environment through ram pressure stripping, which you may have heard Minnie or Salem's talk earlier at the ITC luncheon about this topic, thinking about the halo gas density of the Milky Way and how as these galaxies move through it, there is a hydrodynamic effect that's removing gas from these systems. But what's a little bit puzzling is that Cetus and Tucana, which are two dwarf spheroidals, are sitting out at very large distances, more than 750 kiloparsecs away from a Milky Way type galaxy, so they seem to disobey this morphology density relationship. But the ANCS survey, which was an HST survey looking at dwarf galaxies out to about 4 megaparsecs, finds that this kind of relationship is true for all dwarf galaxies. So dwarfs that have become gas poor, generally speaking, are found in clusters or around massive hosts. Whereas the gas-rich galaxies are generally sitting in very isolated regimes. So there seems to be a very strong environmental dependence in the relationship between dwarf irregulars and dwarf spheroidals. Okay, so another kind of manifestation of this is you could look at the fraction of galaxies that are quenched, so they're not exhibiting star formation. And you look at that with respect to the distance from a massive host. So this was a survey that was done by Marla Jiha using a reprocessing of the SDSS survey. Basically, she found that all dwarf galaxies, now these are slightly more massive, so not really dwarf spheroidals, but rather dwarf ellipticals should certainly be included in this survey, and dwarf irregulars that are forming stars, et cetera. Basically, she found that all of these galaxies that are at larger distances than about 1.5 megaparsecs are all merely forming stars. There's no indication that these galaxies are quenched by other processes. So it really is a very strong environmental dependence that is causing the gas to be removed and star formation to be shut down. In particular, this means that outflows are not, although they are very important in removing metals from these systems, are not sufficient to quench them entirely of star formation. Okay? Otherwise, we should see them. Right? They don't exist in the field. All right, so we're kind of drawing a picture of all these dwarf galaxies are somewhat related. These dwarf irregulars and dwarf spheroidals follow similar scaling relationships, and environment seems to be the critical factor in terms of explaining their relationship. So in traditional pictures, we can think about environment about a massive host, an M31 galaxy or a Milky Way. But I'm going to add a little bit of a twist to this and say that you could also do this in the environment about a dwarf host. The second relationship that I care about is between these dwarf irregular galaxies that are merely forming stars and BCD phase. This is the starburst phase. How are those galaxies related? And I think this has a lot to do with dwarf mergers and interactions. So first of all, let's talk about environment. So as I mentioned, ram pressure stripping is a very efficient way of removing gas from a system once it's entered into a high gas density environment. For example, a cluster. So these galaxies are Virgo cluster galaxies. This is NGC 4402, which is kind of a canonical case of ram pressure stripping in action. And what you're seeing here is the gas contours overplotted the stellar content here. And you can see that the gas disk is truncated relative to the stellar distribution. In fact, not only is gas removed, but so is dust. Right? So you can see these dust lanes are actually going out to about a kiloparsec or so from the disk plane of this system. Now, if this is that efficient on a massive galaxy, it certainly should do some pretty large damage on a dwarf. And this is an example of a dwarf galaxy, kind of an SMC analog, that is moving through the Virgo cluster. And what you're seeing here is a tail of star formation trailing behind this galaxy. So this galaxy is being ram pressure stripped, gas is being pushed back behind it, condensing, forming stars. Those stars then stay where they are. Gas is being removed even further, right? Because this is a hydrodynamic effect. So you get this tail of star formation trailing behind this galaxy. Now, certainly this is a cluster environment, and this process is expected to be quite efficient and quick. However, what happens in the case of a quenching timescale? What is the quenching timescale for dwarf galaxies around our own Milky Way? I mean, how efficient is this process? Over what timescales does it occur? So although we've kind of got the sense that, yes, there's this obvious density morphology relationship, so ram pressure stripping has to be involved. We don't really know the details about this process yet, even though this picture has been around for a very long time. So I think one way to attack this is to get accurate orbits for our satellite galaxies of the Milky Way. And recently I've been involved with a project to get proper motions of Leo 1. Leo 1 is the fastest moving satellite of our Milky Way galaxy. is sitting at 260 kiloparsecs, and its radial velocity is 170 kilometers per second. Right? That's not even including tangential motions. This is just radial. So we've always known that it's a high-speed galaxy. It is a classical dwarf spheroidal, right? It's got very low gas content. Its stellar mass is like 6 by 10 to the 6. Its velocity dispersion is on the order of 9, 10 kilometers per second. So it's a dwarf spheroidal. But what about its orbital history, and where has it been in the past? And at what point was it actually accreted by the Milky Way? So we can use HST to determine proper motions for this galaxy to accurately get three-dimensional velocity vectors, not just line of sight. This is work that I did with Tony San. We have a 5-year baseline for the Leo 1 galaxy, and we're able to observe motions of stars over this baseline with respect to background galaxies, and got out a tangential velocity of 100 kilometers per second. So the total net velocity of Leo 1 is 196 kilometers per second. And it's moving really fast. Now, with this velocity at that distance, it's close to the escape speed of a 10 to the 12 Milky Way Milky Way halo. So what I can do then is take this velocity vector and with the associated errors, and compute orbits backwards in time, assuming a model for the Milky Way. So today, here, this is the time of Leo 1 as a function of its distance from the Milky Way, going backwards in time. So today is here. This dashed line indicates the virial radius. So if Leo 1 starts today at 260 kiloparsecs, it had its paracentric approach at a time about 1 gigayear ago, and it had its infall into the Milky Way 2.3 gigayears ago, and really then it just goes off to very large distances. So the likely scenario is that Leo 1 is on its first orbit around the Milky Way. Now, what's interesting is when you compare these times, which don't vary much with any of the model parameters or even the error space associated with the velocities. And what you get out is, and you compare this time with star formation history of Leo 1. Now, this is the advantage of the local group, right? You have galaxies that you can resolve into individual stars, and you can get color magnitude diagrams and detailed star formation histories. We know that Leo 1 had its last major burst of star formation about 2 billion years ago. Now, this means that on infall, Leo 1 had gas and was forming stars, which means it was a dwarf irregular galaxy, right? The last gasp of star formation occurred 0.5 billion years ago, right, somewhere around here. And today is a dwarf spheroidal. So what this means is that you've got 1.5 billion years to quench that galaxy. So for the first time, we have an actual time scale for which we can test models of round pressure stripping, and this is the subject of ongoing work. But I think this is the advantage of these high accuracy proper motions and thinking about these extreme galaxies. But Leo 1's a classical dwarf spheroidal, but we know that upon infall, it had gas and it was forming stars. Okay, so environment, this transition between an irregular galaxy and a gas-poor galaxy, dwarf spheroid, doesn't just involve a loss of gas and a quenching of star formation. It also involves a morphological and kinematic transition from something that was potentially rotation supported, something closer to a disk, to now something that is dispersion supported and more of a spheroid. Now, the classical example of this process is probably tidal stripping, right? And tidal stirring. So the idea is these satellites are in orbit around the Milky Way. Tidal forces are then now, messing with them, basically stripping off material and also changing their internal kinematics. So a lot of these ideas have come more recently from Evo Lokash and Stelios Kazantzidis, and this model for tidal stirring in the formation of dwarf spheroidals. Now, traditionally, this picture has really focused on, for example, the Sagittarius Dwarf Galaxy. Sagittarius Dwarf is located about 20 kiloparsecs away from the Milky Way. It's a classical dwarf spheroidal, albeit on the far massive end of that spectrum. It has a large set of debris streams that seem to wrap around the Milky Way, and these have all been observed. And what we can then do, and this is what's been done by Katherine Johnston back in 2005, is to model the orbit of Sagittarius Dwarf such that it can reproduce these streams in a tidal stripping model. Recently, there's this paper by Vasily Balakirev, which suggested that there may be other additional debris streams, so these orbits may have to be revised. There may be precession. All these new details are coming out from about the Sagittarius Dwarf. But one of the things I think is most interesting is in this paper back in 2010, you can add up all the stars that are in this debris stream and put it all back together and ask the question, how massive was the progenitor of the Sagittarius Dwarf stream? And it turns out to have a luminosity that's close to that of the SMC. It's actually not that small to begin with. And if that's the case, then it probably had gas, it probably was forming stars, and it was probably a disk. So most of these models that have looked at the debris field around the Sagittarius Dwarf have assumed that the galaxy, the progenitor, was a spheroid. Now, in 2010, Jorge Peñarubia asked the question, well, what if Sagittarius Dwarf was in fact a disk galaxy? And let's redo this analysis. And what he finds in the end is that he still gets a velocity gradient in the central regions of 20 kilometers per second. And that's a problem because that's inconsistent with the idea of it being a dwarf spheroidal galaxy. So what on earth was the system upon infall? And I think there's a lot more work that needs to be done about how this whole tidal stirring process actually works and how, for what time scales and how efficient it is at turning a disk-dominated galaxy into a spheroid. And I'd like to want a bit of advertising. I'm part of a large Spitzer program called SMASH that's PI'd by Katherine Johnston to look at distances to the stream in the Sagittarius dwarf, of the Sagittarius dwarf, and also the core of the Sagittarius dwarf, in addition to a number of other objects in the local group, using RA Lyrae. So it turns out that in the mid-IR band, and particularly using IRAC on Spitzer, the distances to RA Lyrae can be determined to a very high degree of accuracy, out to about 2%. And this is because the period luminosity relationship for RA Lyrae in the mid-IR is quite stable, like ultra-precise stable. So you can actually get out 2% distance errors. And so we have about 20 fields in the Sagittarius dwarf core, and the idea there is to get out the three-dimensional structure of the Sagittarius dwarf itself. And that can be used to test models of whatever the progenitor was over a series of tidal stripping events. So we're really trying to understand. So like I said, we have this picture of ram pressure stripping, tidal stripping. We know in some way it creates dwarf spheroids and explains this transition between a dwarf irregular and a dwarf spheroidal galaxy. But all I want to point out is that in the details, we actually have a lot more to learn. Now, I've presented this process of tidal stirring, and you can understand the concept of if you have a dwarf host and a smaller galaxy, you could get tidal stripping in action. And so it's conceivable that, for example, you can get tidal streams around a dwarf host. However, the other idea is ram pressure stripping. You have to remove the gas from this system. Dwarf galaxies aren't known to harbor massive X-ray halos. They're not known to have efficient ram pressure stripping as a galaxy moves around it. Yet, this system, NGC 4449, is a LMC type analog, although it's undergoing a starburst. And over here was found a very faint companion. Right? This is down to the R-band luminosity minus 13.5. This is close to a Sagittarius dwarf kind of magnitudes. So this thing appears quite elongated. This is sort of blow up of it, but the core is somewhere in here, and it certainly looks like it's tidally stretched. We know that it's associated with this galaxy. There have been color magnitude diagrams, tip of the red giant branch distances, so we know they're roughly at the same location. The luminosity ratio between these galaxies is something like 1 to 50. So we're talking about a host that is far substantially more massive than this lower mass galaxy, right? Which why again the tidal stripping scenario makes sense. But if you actually look at the gas distribution of the system, so here's the original galaxy. There's this huge gas disk that's surrounding NGC 4449. And down here is that perturbed galaxy. And you can see that it actually, down to the sensitivity of the survey, which is column density is about 1019, this thing doesn't have any gas. So it seems that you can, in fact, create, or at least the gas fraction is less than 10%, which is way below what you would normally find in the field. This galaxy is nowhere near a massive system. There's no other ambient medium, not a cluster, et cetera, that this small thing could be moving through. So how do you form a gas-poor, tidally distorted thing around a dwarf galaxy? So what I actually think is going on in this, and this is sort of theory and speculation, but it's something that I've been working on with regards to the Magellanic Clouds, is I think that this galaxy has been moving through in an orbit that takes it through this H1 extended gas disk. Now this distance is quite large. I mean, this is about 20 kiloparsecs or so in diameter. Right? You don't have to have an impact parameter that takes you right through the center to do this. And the column density, or the three-dimensional density of the gas in this neutral phase, is much higher than if it were moving through some ambient medium of this hot halo of the Milky Way, for example. So you could imagine that repeated orbits that takes it through this gas density, this gas disk, can actually remove gas from the system quite efficiently. But the question that remains is, how often would you expect this configuration to occur? What kind of orbits are required to do this? How often do we find dwarf galaxies in paired configurations? And that's the subject of my current work, which I'll discuss in a bit. So I've talked about environment in terms of explaining this gas-rich to gas-poor transition and how this can occur in a Milky Way environment, but also could potentially occur around a dwarf host. The other types of galaxies I'm interested in are dwarf irregular galaxies that are then undergoing a star burst. Now, what happens in a starburst phase? What's triggering it? And the canonical example of a BCD, a blue compact dwarf galaxy, is the system 2's Wiki 40. So 2's Wiki 40, this is an optical image here showing the core. So all the star formation is occurring in a 2 kiloparsec tiny region here. But it's a starburst and it's quite substantial. And then there's these gas contours that are showing this distribution out here. So BCDs in general share a very common property, and that is that the H1 component of these systems is generally extremely distorted. And it's also extremely centrally concentrated. Well, maybe not in the center, but at least there's definitely a concentration of gas and stars. Now, if you zoom in on the inner regions of this galaxy, what you find is that it seems like there's a double core, and there are actually two tidal tails that seem to be going out in two different directions. So the idea behind this system is that it, in fact, is a merger between dwarf galaxies that you can actually see in the optical. So the idea has been presented, and this has also been worked by Kenji Becky and a number of other people, is the origin of BCDs may be related to mergers between dwarf galaxies, starbursts being driven by an interaction between two systems. So this is a system that I mentioned before. This is Zwicky 18. It's the most low metallicity galaxy that we know of, or at least one of, and it's undergoing a starburst in this central region here. The starburst is fairly recent. For the most part, this galaxy doesn't seem to be particularly chemically evolved. It doesn't look like it had many starbursts along the way. What's particularly interesting is that if you look at the kinematics of BCDs in general, it appears that the rotation curve of these galaxies is extremely steep. So this is looking in this inner region and then just plotting the rotation as a function of distance. Typically, most dwarf irregulars have much flatter profiles. So this is related to this cuss-core debate that's been going on and raging in cosmology and in the field. Particularly the idea that dwarf galaxies appear to have fairly chord profiles where the rotation curve doesn't rise as steeply. This seems not to be true for systems that are undergoing starbursts. Now, one of the solutions to the cuss-core debate is that potentially starbursts and outflows are removing material from the inner regions, wherever this rotation curve is, out to larger distances in a non-adiabatic way. And in that case, the dark matter potential, or the potential of the galaxy changes, and the orbits of dark matter particles would change in response to that. And you can actually flatten out the inner cusps that you would expect from an NFW profile and create a core. But these are the most star-bursting dwarf galaxies around. These are the ones with the highest star formation rates, and they seem to be doing exactly the opposite thing, where you have all the gas that's being funneled into this region fueling this burst of star formation, and you have a very steeply rising rotation curve. Now, kind of the jury's out in terms of what all of this means together, and I have to think a bit more deeply about it. Certainly we can discuss in the discussion section later. But I don't think this necessarily supports this theory that starbursts and outflows in dwarf galaxies are responsible for these chord profiles. Okay, so I want to talk a little bit in the last few minutes about my own current research. This is this Tiny Titan survey. And I'm working with a large number of people: Dave Patton at Trent University in Canada, Nitya Kalivailil at UVA, Mary Putman at Columbia, Sabrina Stierwalt, who's a postdoc at UVA, and Kelsey Johnson. And of course, the illustrious team here with Lars and Mark and Paul Torrey and Vicente. So what I'm trying to do is look at cosmological simulations and also to look at multi-wavelength observations of isolated dwarf groups. So these are groups of dwarf galaxies that are nowhere near a massive host. And the idea is to understand what are the processes in the evolution of dwarf galaxies in dwarf environments, not anywhere near a larger galaxy. We know already that environment will have a significant effect on the evolution of dwarf galaxies. So we want to basically take environment out of the equation. So I'm looking at galaxies that are out to about 100 megaparsecs, and the idea is to understand specifically the dwarf galaxy merger sequence. What are the properties of these dwarf hosts? What are their baryon content? And also, so we can understand the baryon cycle of dwarf galaxies and star formation in very extreme environments. The advantage of using the illustrious simulation as well is that I'm able to look at the pair frequency. How often do you find dwarf galaxies in paired configurations? What are their typical orbits? So for example, that scenario that I showed where you have this dwarf galaxy with an extended gas disk and a companion on a fairly eccentric orbit that takes it through even the outskirts of that gas disk, that requires a fairly specific orbital configuration, high eccentricity, low impact parameter. How often does that happen? We actually do have the capabilities to answer that question through this survey. So here are a few examples of, I guess, a kind of a merger sequence of dwarf galaxies. The top here, you have the closest pairs that we have, about 0.85 kiloparsec separation. It's basically two cores, and you can argue whether it's really one galaxy or not. But then you can clearly see, as these galaxies get to larger and larger separations, but what you can see is that there certainly are tidal structures that seem to be emanating from these systems, clumps of star formation that are being induced, even at distances of 50 kiloparsecs. Right? So the dwarf galaxies do seem to be affecting one another. And again, there's no massive galaxy anywhere nearby. So really, these systems are doing it to each other. So these are isolated in the sense that they're more than a megaparsec and a half away from a massive host. And they have stellar masses ranging from 10 to the 7 to about 5 by 10 to the 9 solar masses. Right? So basically a Sagittarius dwarf, maybe a little bit more massive than that, all the way up to basically the extreme of an LMC. So in the end, in the Sloan survey, out to these distances, we have 170 dwarf groups out of the 3,000 or so isolated dwarfs that fit this criterion. most of these are also in pairs. So what we're trying to do then is take those pairs that we've identified in Sloan and then follow them up with H1 observations and also H alpha. So what I'm showing here are some of the H alpha observations that are coming out. This is using Bach 2.3 meter. And you can see that star formation is extremely clumpy in these galaxies. And this harks back to the original statement that I said why these galaxies are interesting. We're not talking about a global mode of star formation. We're talking about star formation that's being dominated by these 5 clumps or so that you see in this one particular galaxy. But not only do you see these clumps in star formation in this one system, there's also a tail that's going here. And this system actually has a bridge of star formation that it seems to be occurring just between these 2 galaxies, which is a completely different regime. This is probably created by a very close encounter between these 2 galaxies. It's star formation in a very low metallicity environment, but it's probably an environment dominated by shocks, which is in a theoretical point of view, a regime that no one really looks at all. So there's a lot of different kind of synergy between the observations and the theory that will come out from this project. So some preliminary results from the comparison between the Sloan pair survey and the illustrious cosmological simulation. So this is just using the dark matter only statistics. And what's plotted here is the stellar mass of the primary of this dwarf group as a function here. And then this is the projected separation between that massive primary and its companion. So these are all dwarfs in general. So in Sloan, we found that about 9% of all isolated dwarfs are found in a group. And in the illustrious simulation, we find a number of about 7%, applying the same observational cuts and techniques. So at first glance, at least, the numbers seem to agree quite well, which is an interesting cosmological probe on itself. I mean, we've thought about the missing satellite problem, and we have solutions to that problem which involve, for example, environmental effects, ram pressure stripping, disk shocking, all these other processes that could explain why we perhaps don't see as many dwarf galaxies as you would expect. But in the isolated environments, you're not going to have the same sort of environmental constraints to help you out and explain the dearth of dwarf galaxies at these mass scales. So if these numbers didn't match at all, it would have been an interesting result. But the fact is, so far, seems things work out pretty well on at least the mass scale of something like an SMC and an LMC. But it's not just that they seem to agree quite well in terms of the numbers. Overall, the distribution in terms of projected separation, for example, of these pairs, generally speaking, has a pretty good distribution and comparison that seem to match quite well. Now, there's still a lot more analysis to be done with these kinds of dwarf pairs, and I have a feeling that there's going to be some other problems that will come out, for example, in kinematics. So it'll be interesting to see what kind of orbits do you actually expect to come out from this simulation compared to what we actually see in terms of projected velocity and et cetera. So I'm just going to finish up here with an overall summary of dwarf galaxies. So I think that dwarf galaxies, with my definition, I've stated have visual magnitudes fainter than -19. They have rotation curves that peak at values less than 100 kilometers per second, and they have metallicities that are lower than -0.4. These galaxies are the most numerous class of galaxy in our universe, right? And it's if we want to understand galaxy evolution in general, you can't just ignore the most numerous class of galaxy in the universe. And I think that it's right now that surveys actually have the capabilities to probe the properties of the ISM of these galaxies in more detail fairly recently. They specifically allow us to probe star formation in very metal-poor environments. And this is interesting from a theoretical point of view. And it's also interesting to understand star formation at the very earliest epochs of the universe. Now, the dwarf galaxy term, as defined here, is a very broad classification, and there exists an entire zoo of dwarf galaxy types. But these dwarf galaxy types do appear to have evolutionary links. And it's believed that, or at least I hope I've shown, that specifically the relationship between gas-rich galaxies and gas-poor galaxies appears to be dominated by environment as the major cause of this evolution, ram pressure stripping in particular, also tidal stirring events. But again, this does not mean that you need to necessarily have a massive central host in order to incite this transition. It's possible that a dwarf galaxy, a massive dwarf, could in fact be the progenitor of this or cause this transition itself in terms of tidal effects and also ram pressure effects if the smaller companion can actually go through the gas disk of the galaxy itself. Now, the interaction or the relationship between dwarf irregulars and the starburst phase appears to be driven by mergers and interactions between dwarf galaxies. But very little is known theoretically or observationally about the merger sequence of dwarf galaxies, and that's the subject of my ongoing work in the Tiny Titan survey. Great, so thank you.
We have plenty of time for questions. If anybody has any.
I have a comment and a question. So the comment is about the mergers of dwarf galaxies. Mm-hmm. A few years ago, there was a dwarf galaxy meeting at Heidelberg, and I was presenting there the first evidence for mergers between dwarf ellipticals from the existence of the kinematically decoupled cores inside some of the dwarf ellipticals in Virgo. Mm-hmm. And Ben Moore was laughing at me. He said, "It's impossible." So now I'm very happy that you're showing it as well, and from a totally different perspective.
That's right, absolutely. And I think you do expect those things to happen. The tricky thing with dwarf ellipticals, I think, is that those systems are, generally speaking, in clustered environments. So it's, there's a lot of there's a different dynamical environment, right? But regardless, the fact is that dwarf galaxies do interact when you've seen them.
And so the question is about the scale relations. Probably you're aware of this long-standing dispute between Cormindy and anti-Cormindy groups. So one is saying that there are two different scale relations for giants and dwarfs, and the other one, presented by Pat Cote and Alistair Graham, they say that actually it's one relation. It's a relation between the the total mass and the source concentration index that is projected to the parameter space presented by Cormindy, and it results in two sequences. So what is your view on this?
Yeah, so I do fundamentally think that they're distinct. And I think that the process of how those galaxies form is distinct. And I think that's the explanation for it. So I don't believe that it's, generally speaking, I mean, that argument would then imply that all galaxies need to follow this kind of relationship. But I do think that fundamentally that elliptical galaxies are distinct from dwarf spheroids.
Have you found a supernova remnant in any of these low-mass, gas-rich systems? And if so, what does it look like?
I haven't looked at, no, I don't know. I'm not sure.
Because with these very low-mass systems, I just wonder if they wouldn't just blow out of the galaxy altogether and you would lose a lot of your enrichment.
Yeah, so I mean, this is what they have these huge super bubbles, right, in these galaxies. In the Onsian, generally speaking, all dwarf irregulars have these. And so it is expected that, basically the metal enrichment is blown out and lost. And there's a starbursting dwarf. It's just pretty spectacular if I can find it. But you do expect to have pretty strong winds, and these are basically very efficient at removing gas from these systems. It's this one. So this is NGC 1569, and it's a pretty crazy starbursting dwarf, which hasn't been caught having an actual active wind and seen in X-rays.
Could you make it dark for a moment? It's such a nice night.
Yeah,
Could you make it dark for a moment?
Can we turn off the lights?
Yeah. So this galaxy has been looked at in terms of its actual metal outflow. So Crystal Martin has written a paper about this, and you can actually get mass limiting factors at most of a factor of 10 or so. But they basically concluded, and this is in agreement with the work by Evan Kirby with this metallicity-luminosity relationship, that dwarf galaxies are very bad at retaining metals. So all of this just flows out.
Going back for a moment to your slide about the dwarf spheroidals and the debate about the cuspy core problem.
Oh, yeah.
And you suggested that I think the two you showed on that plot both go against the theory that starbursts kick out the baryons from the center and help smooth the core. I was just wondering if you know what statistics we have on that. In other words, of the dwarf spheroidals where we do observe the smoother cores, how many of them are expected to be starburst versus not? And does this conclusion based on these two, that the theory can't be really correct, apply if you look at the sort of all of those that we do know?
So we're talking about dwarf irregulars and starbursts. These are the ones with gas. And the core cusp debate definitely goes down to the dwarf spheroidal regime where things don't have gas as well. But some of the debate has been raging about these dwarf irregular galaxies because you should be able to see this process kind of ongoing. I would definitely refer you to Federico Lelli's recent paper, 2013, where he's basically asking about the question of what are these starbursting dwarfs, how often do you see them like this, and what do they actually evolve into? And it turns out that there are dwarf irregulars that have fairly large rotation curves, steeply rising rotation curves. And so he's suggesting that BCDs, these starburst phase, will then evolve into those types of galaxies, rather than forming a core profile, right? So that's where the differences lie. And so these systems, generally speaking, BCDs all show this steeply rising rotation curve. At least Federico is claiming that all of them do. Dwarf irregulars, so some of them have the core profile, some of them don't. And so the question is, what's the difference between these two classes of galaxies? And is one related to, for example, the starburst phase and what happens to this galaxy after, what's the post-starburst, dwarf galaxy? What does it look like at these mass scales? So that's kind of the questions we have to look into. The Little Things survey, which is an H1 VLA survey of these dwarf galaxies, has looked at the rotation curve of these systems, and this is what's been fueling the debate because they've been finding many dwarf irregular galaxies that have these types of profiles. But it does seem that during the starburst phase, which is when all of the blowout is supposed to happen, you seem to have more of a not a chord profile. Of course, this could be at the peak merger. These are also late stage mergers, so maybe at earlier times the potential isn't quite so steep or something else happens. But these are really low metallicity systems, so you're kind of approaching the environmental conditions you would expect for the earliest galaxies. And it does appear that to drive a starburst in a dwarf galaxy, you need to funnel in a lot of material into a very concentrated region, which will necessarily imply that the rotation curve has to be quite steep.
Thinking about the early universe and these dwarf galaxies as analogs to the early universe, it seems to me that in the early universe there are very few massive galaxies around, and also there simply hasn't been enough time for any interactions to do very much. So I'm thinking that, am I wrong in thinking that the totally isolated ones are the ones that we want to look at as the...
Yeah, I totally agree with you. And I think that's kind of the motivation of my looking at these, these isolated dwarf galaxy pairs, is the idea of thinking about mergers and interactions at the earliest phases of the universe. I mean, these are our only local probes of that process, short of, trying to looking at them more directly with lensing surveys and things like that. And especially, these are really not chemically evolved. If you actually looked at the star formation history of these dwarfs, particularly the ones in the burst phase. So these are all slides that I wanted to include, but I thought I would go way over time. Anyways, so here's 1 Zuki 18, and right now it's going through this massive burst, but in the past, there's nothing really going on in this galaxy. So it seems to be really not chemically evolved. And so if you want to think of a local probe of something of a very chemically unevolved galaxy, these are the systems we're looking at.
Well, it is still a metallicity of a tenth.
Yeah, that's right. So, absolutely, right? This is about as close as we can get, but I totally agree that these are not direct analogs in any, in that way. But, when we're trying to develop theories about how star formation should proceed and how efficient should it be, these are the systems we have to be looking at. And that's why right now there's a big interest in these low metallicity, low mass galaxies.
Well, but to be fair, the redshift 5 and 6 galaxies are also metallicity of a tenth or maybe more.
Yeah, and I mean, for these mass scales, it doesn't matter what redshift you look at, dwarf galaxies are always the most numerous class of the galaxy, right? It's not just today, it's at all times. So these are the kinds of galaxies that we need to understand.
Yeah, do tidal dwarf galaxies, the ones formed in tidal arms, satisfy the same scaling relations?
Oh, that's a good question. I'm not actually sure if they entirely do, but one of the really differences in those populations is that you don't expect multiple episodes of star formation over time, and they're formed in a very distinct way. They shouldn't have dark matter either, right? So, but that's an interesting point. I'm not sure how they would fall into all of those plots. I imagine they would fail this metallicity-luminosity relationship, though, pretty dramatically. That would be interesting to see.
You had one survey called 11 Houses.
Yes.
Does that refer to it?
Right. Yeah, so that's H alpha UV survey of nearby galaxies out to about 11 megaparsecs. So I do know what I put on my slides. Yes, LR, thank you. So that's a really fascinating survey, and the dwarf galaxy part of that survey was led by Janice Lee. And she's been looking specifically at starbursting dwarf galaxies. And this is really where the statistics of starburst have come out from. And it's a pretty fantastic survey when you're actually looking at these properties. And really just showing the properties of the properties of those dwarf galaxies as a population. And that's the first time, that was back in 2009 where she wrote those papers. And then since then, Federico Lelli and other people have been doing follow-up works on understanding starbursting dwarfs.
One gets the impression that galaxies merge as the universe evolves. What do you know about the fraction of dwarf galaxies as a function of time?
Yeah, that are undergoing mergers, you mean? Yeah, so right now the fraction is about 10% in terms of in an interaction. But certainly that fraction must have been higher at any given time of interacting dwarf galaxies. Laura Salas has actually done quite a lot of work from a cosmological point of view, of thinking of the mass buildup of dwarf galaxies and their mass functions today. So I think that I imagine that these processes are important, but I don't actually have a number in terms of how often this occurs over time. The idea is to try and see if today we can reproduce the interaction rate. If that interaction rate seems to agree, and it seems to so far, this 9 or 7%, then we can use merger histories of these galaxies, which we have, the merger trees, and follow this backwards in time. But I don't want to go into that step until we can reliably say something true about them today, right? You get that wrong, everything's wrong, right? So, but I think the jury's still out on that question.